Hello there, and welcome back. This is a tutorial series on how to reconstruct 3D magnetization from tomographic electron phase images, and I am Maurice Schillinger. In the previous episode, we saw how to install all the necessary software for model-based iterative reconstruction, and in this video, we'll look at how to separate the electrostatic and magnetic phase components from the phase images. In my work, I use electron holography, and my raw data are holograms. As you can see, when we zoom in, we can see the interference fringes. I usually process them using HoloWorks to get the phase images. I will leave that up to you to use your preferred method on how to extract the phases in your experiments. And that's what the phase images look like. To be able to separate the electrostatic and magnetic phase components, we usually take a second image after we have rotated the sample 180 degrees. Now, before we can get to the automated processing part, where we do the alignment and correct for distortions, we need to take the upside down image, we need to mirror it, and it usually helps to rotate it to be approximately at the correct orientation as the first image, and it also speeds things up if we can have both images be the same size, like so. And this we can save as being the second side of the phase image. Okay then, with that in place, let us restart our package manager we installed last time. Let's activate our environment. Let's launch Jupyter Notebook, because that's where all the demos for the software are written. Now then, previously we have the source code in the downloads folder. We go under demos, Magnetisation Reconstruction, and let's open up phase separation. Let's just simply import everything we need to import, define in which folders we store our phase images, and this expects to have two phase images in each folder corresponding to the right way up and the upside down phase image. And then let's have a quick look at it. We're going to select folder 1, which in this case corresponds to a tilt of 20 degrees in the tilt series, because that one looks nice. And we're going to define all the file locations and load them. We can also input the fringe spacing in these images. Then the software will automatically determine what is an appropriate pixel size to be used in the reconstruction. But in this case, the size is already adequate, so it makes no changes. And we can see that we have, in fact, opened up our phase images in Python. Then, for the alignment, we can either give it pixel values of which part of the image it should use for the registration, or we can use a semi-automated approach where we just select an area in the overlapping images that we want to be aligned. And then we keep going with those. And for the alignment process itself, it starts by first detecting the edges of the sample in both images. If this doesn't quite work, we can tweak the values up here to make sure that we isolate the sample edges instead of the majority of the smaller features on the inside. And then once the edges have been detected, it identifies matching parts of the image which seem to be unique, and tracks how they have moved between each image. And using that, it calculates a transform that aligns the images. There you go. That's our phase images aligned. We can then calculate what the corresponding magnetic and electrostatic images look like. And you can also save them here if you want, but I will not at the moment for the purpose of this demonstration. And then before we go on to the full reconstruction, we might want to also speed it up, and we also need to clean these images up. We still have holes from what we masked during the initial part, which need to be filled in, and we should also apply a bit of smoothing before we go to tomographic reconstruction, which is what the next part of the code does. We choose to ribbon them 4 times. This will give us nice small images with just enough information for 3D reconstruction without causing too many problems. And as you can see, the results of running that cell is that we first get a confidence mask, which tells us which parts of the images we trust. And as you can see, there's a little bit in the center, which we previously masked as being a phase unwrapping error, which will not be included in the final calculation. Most of the image will be used in the calculation, and there's also some parts of the edges which are not included either. The way this is created is that it first uses the masks it came with, then expands them like 3 pixels from the edge, or by however much we specify in the erosion depth, then fills in all the holes, applies smoothing, a small Gaussian to remove high frequency noise, a median filter to remove bad pixels, and the result of the smoothing is that we get cleaned up magnetic and electrostatic phase images. Now that is done, we should also define a mask which tells us where magnetic material is in the side of the sample. So first we remove the background from the electrostatic phase image. So the background is nice and flat, very close to 0 all around. And then we see that the edge of the sample is around, -3, -4 all the way around. So we set that threshold here, and it applies it to the image to create a mask which tells us that magnetic material is located, well, where it's colored right, and the rest should be vacuum. Okay, and with all the masks in place, we save them in a dataset structure, which is inherited part of the reconstruction code, which keeps all the phase images and masks and the confidence mask in one place to be used later once we get to doing the 3-dimensional reconstruction. And at this point, if we want, we can also reconstruct the magnetization of the flat image. It will be an integrated reconstruction, as in what we see is a flat reconstruction instead of the full sample, but this is the estimated, well, I guess, thickness sum of the magnetization. And as we can see, it shows us where we expect the main walls to be. It shows us that the legs of the sample are mostly uniformly magnetized. But this is not very quantitative and tends to vary a lot, because this does not account for the geometry, which is why we will go do the 3-dimensional reconstruction in the next videos. And yes, we can also look at a summary of all of the processing, showing us that we have a phase map with phase measurements, with a mask telling us where the sample is, and also a confidence array showing us which part of the measurements we trust. Now that we've done that, we can go back to the first cell, choose a different folder to process, and we should do this for every single tilt angle before we proceed to doing 3-dimensional alignment, which will be in the next video. Thank you for watching, and see you next time.